Hello, and welcome to this Tungsten Replicator Masterclass training session, where we're going to look at replicating into data warehouse targets. My name is Chris Parker, VP of Customer Success here at Continuant. So in this course, we're going to look at the replicator flow into three specific data warehouse targets: Hadoop, Redshift, and Vertica. We'll also look at the specific prerequisites required for those targets, and then we'll look at some of the example configurations you can use. So replicator flow. So first of all, I'm not going to go into detail on the extraction process here. We have covered this quite a lot in some of our other training sessions. But just to summarize, the extractor will take binary log information as it is processed by MySQL. We'll extract that into what we call THL. Those THL log files are then picked up by the Applier processes, which work on them differently depending upon the type of targets that we are writing into. So first of all, let's look at Hadoop. The Applier process will take that THL and it will write that THL into CSV format, specifically recognized for the HDFS. A JavaScript process will then take that CSV and it will load it into Hadoop for you, performing a materialization on the data to ensure the consistency in that final end target. How does the materialization work? On the left, we have a simple two insert statements and an update statement. In the CSV, these will get written out in the format shown here on the right-hand side at the top in what we call a staging table. So the insert will be there as an insert. We'll have an opcode of I for insert, the sequence number that it was generated as part of the THL, and the ID, or the primary key ID field, in this case 1 for the message hello world. The second insert, second sequence number, ID number 2, and then the message meet continuant. The update for the materialization process. Updates are not a valid statement in the world of Hadoop and Redshift and Vertica, or at least if they are available, they're very inefficient. Data warehouses work better with insert statements. So what we do with an update statement is, first of all, we delete the row. So we have an opcode of D, the sequence number in this case is 3, and the primary ID here is 1. So we delete that row that initially said hello world. And we then reinsert it. In this case, we reinsert the data with the message goodbye world. So that's what the CSV would look like. The materialization process will then collapse all of that down into what we call the base tables, so that you end up with a resulting table output which matches your initial production source table. For Vertica, exactly the same process applies. The applier writes that THL into CSV files. It is then imported into Vertica using the cpimport. We then have a JavaScript process which works via the JDBC protocols to load the CSV data from the staging tables and merge it into the base table. Exactly the same process as we looked at previously with the Hadoop materialization. An insert would be one row in the CSV, an update would be a delete followed by an insert, and it's the same process. That data will get loaded into staging tables. The staging tables are then merged into the base table so that you end up with a true representation of that original table. Redshift, again, exactly the same staging table merge process. However, this time the CSV files that are generated from the applier are loaded up into an S3 bucket using the S3 command. The JavaScript then uses the JDBC calls to load that S3 CSV data into the staging table, and then the same merge process that we previously discussed merges that data from those staging tables down into the base table. And that's it. That's very simply how that data moves from a CSV file into those tables. And this is what we call a batch process, which is very specific to this type of load process. We load batches of CSV files, and those batches are then loaded in batch into those tables. Whereas the OLTP type loads, where we load into MySQL to MySQL, MySQL to Postgres, MySQL to Oracle, that's a JDBC load process where the THL is converted into SQL statements. So they go directly into the database and is more real time. The batch process is near to real time. Delay there can be dependent on a number of properties which you can set. So you can change the replicator to load more frequently but smaller batches, or less frequently and larger batches. The less frequent, larger batches are actually a lot more efficient and will work faster than frequent small batches. And that's just because of the way data warehousing is designed. It's designed to be efficient for those large batches of data. So that's how we make the most of that, by loading up these CSV files in large batches and merging them into your source data. So what are the prerequisites? Well, the extractor has the normal prerequisites we've spoken about in previous sessions. The actual applier host itself, where the Tungsten Replicator is installed, There are still the same prerequisites for Java, Ruby, etc., and all the various network ports that are required to communicate between the extractor and the applier. Additionally, the applier needs to have the various network ports open to communicate to your target, whether that's Hadoop, Vertica, or Redshift. The MySQL database on your source, best practice settings that we recommend to get the most out of MySQL. Additionally, for this type of replication, your source database must be in row-based binary logging. In terms of Hadoop, the HDFS needs to be writable by the replicator user. In Vertica, you need to have user accounts set up, and you also need to source and provide your own JDBC drivers for this. These are the Vertica JDBC drivers that Vertica provide. We don't provide them and ship them with our product, so you need to make sure you have them available. In terms of Redshift, the various user accounts again need to be set up. You need to have an S3 bucket, and you need to have the S3 tools installed on your host so that you can upload to S3. So that's the S3 command or equivalent. And you also need to configure an AWS JSON config file, which I will talk about on the next slide. One key thing to point out here is for replication to work from MySQL to a batch load environment, all of your tables must have primary keys. Without primary keys, we can't guarantee that the correct table, the correct rows of data will be updated when we do updates, deletes, etc. And that's just purely down to the way that the batch processing and the way the data warehousing works. So we must have primary keys on those source tables to guarantee that consistency. All of these prerequisites are in our documentation at docs.continuant.com. So if you need a little bit more detail on these, if you head there, go to the Tungsten Replicator docs, and you'll find all of that information within the chapters of those doc pages. So the AWS JSON config that you need for Redshift, this needs to be created. We don't create it for you. So once you've installed the replicator, you will create this JSON config file, and you'll just need to put in the keys that we have here. Not all of these are necessary, it depends on your use case, but you will need to supply the AWS S3 path. That's the location of the S3 bucket that you want to upload the CSV files to. You then need to supply either one of the AWS access key secret key pair or an AWS IAM role. And that's the roles or the keys that are configured to allow you and give you the permissions to write into S3. We do have some documentation pages that explain what permissions you need. It's all there in our doc pages. We then have the multi-service target, single lock table, and lock table prefix. So Redshift only supports serializable transaction isolation level. That differs from relational databases like MySQL, which is repeatable read by default. So these isolation levels determine the behavior of the database for concurrent access to tables within transactions. So when loading data into Redshift from multiple appliers, this isolation level can cause locking issues that wouldn't manifest itself as errors in the replicator log, and you'll see the replicators going into an error state. In some cases, the replicator will just simply retry and carry on successfully once that lock is released, but on very busy systems, it can sometimes cause the replicator to fall into the offline error state, at which point manual intervention will be required. So if you are writing into Redshift from multiple sources, the first step is to ensure that each applier that you are using has its own set of staging tables. The next approach would be to introduce table locking. So by setting the multi-service target to true, you're telling the replicator that there are multiple appliers writing to this. And what that will do by default, it will enable a single table locking approach. Since the single lock table property, the next one down, is on by default. When this property is enabled, you'll need to create a single tungsten lock table for the process. If you disable single lock table, then you enable the use of one lock table per base table. I know this is getting into quite advanced territory here, but it all comes down to if you have multiple appliers writing into Redshift, then you need to choose whether you have a single lock table or multiple lock tables. And that is depending upon that single lock table property being true or false. So if it's true, which is the default, you will need to create that single tungsten lock table. If you set it to false and you want one lock table per base table, then you will also need to manually create a lock table for every table in your schema. So if you have 10 base tables in your schema, as part of the batch processing, you will also have 10 staging tables. You will also then need to have 10 lock tables. And all of this is explained in our doc pages. I don't go into this level of detail around table locking and lock tables in this particular training session, but we do have extensive notes. So if you go to the online docs and just search for Redshift Applier, there's a lot more information on how this works. So if you are writing for multiple appliers, head there, read the docs, and it will all make sense. Additional options you can supply in this JSON config. There's the Redshift copy options. So that allows you to pass additional syntax to the Redshift copy command so that the CSV loading is like a JavaScript file, and it uses the Redshift copy command to load those CSV files into your staging tables. If you want to add additional options to that valid Redshift syntax, you can do that using that property. Clean up S3 files, true or false. It's true by default. If you set this, once the CSV files have been loaded into Redshift, they get deleted. gzip S3 files default is false, but if you set them to true, then the CSV files will be zipped up prior to loading up into S3. And then the store CDC in, it's a definition table that stores change data from the load. So it's in addition to importing staging and base tables. It's not a common used setting, but it is there so we can store that change data capture information if you wish. And again, I'm not going to go into detail on CDC in this session, but if you look through the docs, if this is something you are interested in, it will be explained in more detail. Now, one thing that is specific to all of these, Redshift, Vertica, or Hadoop, is that you will need to provision that data initially for yourself. So you will need to create the schemas. We don't replicate DDL, we'll only replicate data changes. So you'll need to pre-create the schemas, and you'll also need to preload the schema with data if you are setting up replication from an existing MySQL database that has data in there. How can you do that? Traditional CSV export import. So if you're able to get the data exported as CSV from your source and then load that into your Vertica or Hadoop or whatever as CSV files, great. You could use the replicator. You could set up a separate MySQL instance and set the database engine to black hole. What you can then do is set up a replicator against the temporary MySQL instance that's got the black hole engine running. You can do an export from your MySQL instance, import into MySQL black hole. That will generate binary logs, which will generate THL logs, which the replicator will then pick up and load into your target database for you. Once that load's finished, you can then change the source of the replicator to then start extracting from your proper MySQL rather than the black hole MySQL. If target supports standard SQL, insert statements, etc., you could extract the data from your source MySQL as insert statements and then run that against your target database. Or for Hadoop, you could use the Scoop utilities. How do the objects map? A MySQL database in Hadoop becomes a HDFS directory. A table is a Hive-compatible CSV file. And then a row is a line in that Hive-compatible CSV file. Redshift and Vertica, it's PostgreSQL interface and syntax. So if you're familiar with Postgres, with Vertica and Redshift, it's all of the same commands. And from there, a MySQL instance is a database. A MySQL database maps to a schema. So I mentioned that we don't replicate schema changes and DDL, so you need to pre-create that first. We do have a tool called DDLScan, which will reverse engineer the MySQL objects, and it will create you target-specific DDL, so it will map the data types correctly for the type of target that you are wanting to create. It can be used for single objects or entire databases. Obviously, it must be configured prior to starting the replicator, and you need to run this at least twice for Vertica and Redshift. Once, which will create the base table, which will be an exact replica in terms of column names as your source table. And then you need to run it for staging tables. A staging table will have all of the same column names as your base table, and it will also have additionally 4 prefix columns, which are used by the replicator, which will be the operation code, so it's an insert, delete, etc. It will have timestamps, sequence numbers, and any primary key information. That information is basically stored within the CSV file, so it's an exact table copy of what the CSV file will hold. And then for the locking that I mentioned previously for Redshift, there is a template that will create the lock tables. So that the staging tables by default will be stage underscore xxx underscore and the base table name. The locking tables will be lock underscore xxx underscore and the table name. So you can use DDLScan to create those tables, create them in your target. And then what will happen is that CSV load process, the CSV will be loaded into those staging tables. That's that stage underscore xxx underscore table name. And then the various JavaScript merge processes, depending on the target, will take that data from that staging table and merge it down into the base table. Configuration files, so a typical extractor configuration file. The only additions to a regular MySQL extraction replicator would be the enable heterogeneous service equals true property. This tells the extractor that you're writing into a non-MySQL target, so it will make sure that the THL it generates is correct and accurate for that. You will also need to enable the drop statement data filter and the replicate filter. Drop statement data drops the DDL. We can't replicate DDL, so we need to drop that from THL. And then the replicate filter will enable you to select what schemas, tables, objects, etc. that you want to replicate. You could also use the drop column filter. There's other filters you can add on here, but at minimum, use the replicate filter to select which schemas that you want to replicate. I would recommend if you've got a database with 20 or 30 schemas and you want to replicate them all, then use the ignore schema to ignore the MySQL schema you wouldn't want to replicate across. Or if you only have 1 or 2 schemas that you want to replicate, then use the replicate.do property instead and just list the schemas or the schema table name combinations here that you actually want replicating. And that will set up the pipeline for you. In terms of the appliers, all of these are pretty much the same. The defaults are the same for all of them. The only differences become in the service blocks. So for Vertica, your data source type is Vertica, your replication user and details and port numbers here. The database name for Vertica that you want to replicate into. The batch enabled is true, it's a batch load. Batch load template, the Vertica template we're using, the JavaScript language. And then we have the applier block, commit interval, and commit size. I will talk about these on the next slide, so I won't go into detail on what those mean at the moment. In terms of Redshift, pretty much the same as the Vertica one. We're just using Redshift as the key names there. The default port number for Redshift. Replication host here is the endpoint for Redshift, so that will be your AWS endpoint that you will get out of your AWS dashboard. Again, batch enabled true. The batch load template here is Redshift, and again, the block commit interval and commit sizes. For Hadoop, same defaults. In this time on the service blocks, we have the data source type is file because we're writing to that HDFS. The replicator data source global CSV type is Hive. And then you have the properties there, the batch enabled, the template Hadoop, and the JavaScript load language again. So that's your Hadoop style configs. So understanding block commit. Let's specifically talk about how block commit helps when we're replicating into data warehouses or those other batch load environments. This is applicable to all three, Redshift, Vertica, and Hadoop. So in this case, our goal is maximum throughput, not low latency. Each commit in the database carries cost. So instead of committing every single transaction, the block commit feature groups multiple transactions together and commits them as one. So this comes back to what I was saying at the beginning of how we utilize the better performance of these data warehouse environments by loading in batches rather than single transactional like an OLTP environment. And it's these two block commit parameters that help do that. And it also drastically cuts down on that commit overhead. So the key tuning parameter here is the SVC applier block commit size. This controls how many events or transactions are grouped before a commit occurs. I say events or transactions because one event may be multiple transactions. There's not a one-to-one relationship between a statement in MySQL and an event or a transaction. There could be groups of them. So it's how many events or transactions are grouped. For the batch pipelines, we can safely set this much higher. Okay, so set this to thousands of events per commit if you wish. Isolation between transactions is less critical in these batch environments because this is just loading that data into those staging tables. We can also then enable the applier block commit interval. This adds a time-based safety net, so ensuring that even if the event count hasn't been reached, commits will still happen at regular intervals, preventing overly long uncommitted batches. The lower the commit interval and the higher the commit size, then you could kind of tweak these, combine these two together to get a much closer, almost close to real-time replication. So when tuned, they can reduce the load times, lower the overall system overhead. This is much better for the analytical databases, staging schemas, reporting targets, things like that, where the transaction latency doesn't matter as much as volume throughput. It's all about tuning these two parameters. I always recommend to anyone replicating into the likes of Vertica and Redshift, if you've got the benefit of being able to set this up in a test and development environment, then do it, load test it, and constantly tweak these properties and find what combination of commit size and commit interval works best for your workload, because no two use cases are the same. One customer may find that a really big commit size and a much smaller commit interval works. Other customers may find a smaller commit size and a longer commit interval. It's going to be different for everybody. So play with this, tweak these, and get them set to how you wish. So in summary, what have we learned? Well, we've looked at the Replicator Flow. We've looked at Hadoop, Redshift, and Vertica specifically, and the prerequisites, configurations, and the various things you need to consider for them in terms of block commits and how to tweak and tune these to suit your use case. So thank you for your time today. I hope you found this information useful. Some of it was quite an advanced level, so if you do have any questions, you'd like to learn more, please do reach out to us via the usual support channels, and we'll be happy to help you out, configure this in your own environment, and spend some time working at tweaking and tuning it to suit your needs better. So thank you, and I look forward to speaking to you on a future training session soon. Take care and goodbye.